All right, I had a few questions. Actually, one I forgot to answer yesterday, which was regarding the discussion board. Weird. So, discussion board this week for organic concerns deals alder synthesis. So, you're given the starting reagent. And you can go through three steps. Lambda and CL2, elimination, halogenation, and then elimination again. So already from the Alkynes chapter, this should be pretty familiar to you. So first halogenation, we're going to assume monohalogenation. We're going to get the chloromethyl cyclohexene, 1-chloromethyl cyclohexene. Elimination will get us the 1-methyl cyclohexene. When we add the chlorine, we're going to end up getting both the R and the S forms of this anti-addition to give us the 1,2-dichloro 1-methyl cyclohexene. And elimination here is going to give us 2-methyl 1,2 cyclohexadiene. Now you're asked to react this product with this product. So if you weren't able to get this far, you're kind of dead in the water for the problem. So this is just a Diels-Alder reaction. And I can take this. And symptom of a Diels-Alder here is going to be your cyclohexene. So you got 1, 2, 3, 4, 1, 2, 3, 4, and then with your dienophile, you got your alpha and your beta. Now these are connected by cyclohexene rings because alpha and beta are connected. So what's going to vary here is what's connected to 2 and 3. So we can have a methyl group here. We can have a methyl group here depending on if we define this is the first carbon or this is the first carbon. And for the alpha beta, the same thing. We can have a methyl group or we can have a methyl group. So you've got a couple different options here. The trick to answering this question is that if you look at it, 4 of the compounds contain only 2 methyl groups. So we can only have, our end product is only going to have 2 methyl groups hanging off the rings. Those are your answers. The ones that have 3 methyl groups don't work. The reason they don't work is that these don't have 2 methyl groups to give you a total of 3. So that was the first question I got asked. Again, I'm sorry I forgot to answer it yesterday. Now the other question I got was this morning, actually a series of questions. For Alkynes reaction, for the halogenation XX of addition of alkynes, when writing out the reaction on the test, is it sufficient to write HXCl, HBr, etc. as the reagent and draw the final product of the geminal alkyl dihalate, or do we need to specify that there are 2 equivalents? So it depends on what you're doing. I would say specify if you're working with the 2 equivalents, just to be clear that it's working with 2 equivalents. You can get the same, you can get a different effect working with 1 equivalent. Now that said, I also don't tend to give questions that are that ambiguous, right? So in the packets, it'll specify 1 equivalent, 2 equivalents. In practice, that's super hard to do. So these 1 equivalents, 2 equivalents, they are more hypothetical exercises, more to kind of get you to see what's going on. You would never be given a reaction where you would have to have those types of reaction controls. So yes, I would say if you want to specify between a single halogenation and a double halogenation, you need to write 1 equivalent versus 2 equivalents. But another thing you can say is just excess HCl, and that's the same thing as saying 2 equivalents because that's more than enough to react your alkyne. Next question, when writing out hydration of alkynes, do we need to include both H2O and H+ as reagents? In your YouTube lectures, you have both listed reagents, but I don't see H+ mentioned in the PowerPoints or that big chart with summaries. So this is kind of it's an esoteric question, and I don't mean that in a disparaging way, it's just kind of esoteric. So let's say you have this alkyne, and you add H2O, and the question is, should you have H2O or should you have H2O plus? So when we add the plus, we're implying acidification. But the thing is that water does this already. So we already have H plus present. The question is, do we have enough of it to make this reaction happen? So the answer is we always have enough to make this happen in water. So if we take an alkyne and we heat it up in the presence of water, If we acidify, so we add the H plus to it, this reaction goes faster, so it's an acid catalyzed reaction. But there's no way to get rid of this H plus, because what this H plus does is it tautomerizes. So if we were able to magically stop water from doing this and just run the reaction as is, we would be stuck with the enol. So in the absence of any H plus, so somehow we've magically gotten rid of all the H plus, this would be your end product. But because we have H plus present, we have this ability to run this reaction. Oops. And there's no way to get rid of this H plus because the alcohol here is acidic. So in principle, even if you were to form this enol, it can catalyze its own reactions. And now we have the H plus that can be attacked, and the lone pair can come down, and we get a neutral molecule again. So no, you don't need to write out the H plus. Formally, you'll see that written in notes and textbooks because technically you need the H plus for the tautomerization step. That said, there's an H plus present because you have water because it does this reaction already. And on top of that, even if you were to magically remove all the H plus, so you just had one-to-one equivalency alkyne to water, and you only form the enol is still acidic. And the acidic hydrogen will pop off, and you'll start seeing this tautomerization. It will be incredibly slow, but it will happen. So generally speaking, when you see the H+, it's just kind of there to imply that it speeds up. And actually in Organic 2, we run a reaction to test for the presence of alkynes, and we add acid. It's not because the acid is needed for the reaction, it just speeds it up. Can you provide an example of hydration of an alkyne with your non-terminal alkyne, or does this happen all the time with terminal alkynes? It happens with alkynes. The reason we work with a terminal alkyne is just the easy example. It's also an unambiguous example. So let's say I had this molecule. So I'm just going to draw it weird, and I'll make it an asymmetric alcohol. Make it an asymmetric alkyne. And so I add water and I heat up in the presence of acid, and again, this is just to speed it up. So I have 1, 2, 3, 4, 5, 6, 7, 8 carbons in my molecule. And I'll put the methyl group up here. We can get 2 different ketones. So these are both cyclooctanones, and this would be the 1-methyl, the 2-methyl, and 3-methyl cyclooctanone. So this happens regardless, but the problem with predicting these types of reactions, which is why you see pretty much books and even my notes get in the bad habit of sticking to terminal alkynes, their only way to substitute an alkyne is to either replace the hydrogen at the end with a carbon. So these are really the only 2, okay, you can definitely have acetylene. But these are really the only 3 types of alkynes, one with a 1R group, one with 2, one with 2 hydrogens. Well, this one is symmetric when it reacts, so if you react this with water, you only get one choice, and that is the ethanol. If you react this one, you only get one choice, which is the ketone. Or the aldehyde, or yeah, ketone. This one, though, you get ambiguity because you can substitute here or here. So for ease of making the products easier to predict, typically you'll see terminal alkynes or acetylene reacted with. But if you end up with an internal alkyne, the challenge you get is you're going to end up with 2 products, and it just gets a little more nuanced. But again, it's not because they don't react. Internal alkynes definitely react. It's just that the terminal alkynes are a lot easier. You basically always get one product with those. All right, nucleophilic substitution by alkynes. We draw out both steps nuclear sufficient to give an alkyne and an alkyl halide as the reactants as a strong base as reagent, and simply write out the final product, or would you like to draw out both steps individually? When you write the mechanism, you need to specify they are separate steps because they are separate steps. So when you do the nucleophilic substitution, and let's say you want to do the substitution here. You never want to combine the two of these, so you do need to specify that these are separate steps and that you first form negative. You first form the nucleophile, which attacks the bromine, or attacks the leaving group, and you get that. The reason you need to specify is that if you add this to this, you'll get a terminal alkyne. Or no, you'll get the, you'll definitely get elimination. You'll end up getting the alkene, and this reaction doesn't do anything. So when you write it out, you don't need to write out that this becomes a carbanion, but you do need to specify that this is added in a separate step, because the two of these aren't mixed together and then you add this. This is mixed with this, and then once you've isolated this carbanion, that's when you added the alkyl halide to get the nucleophilic substitution. So again, you do need to write out the individual steps in that you need to specify that this step is separate from adding this step, because adding the three of them together doesn't really accomplish anything. But as far as writing out intermediate products, that you don't need to. You don't need to specify that this is a sodium salt of the alkyne. You can just say that I reacted this with this and then took the product of that reaction and reacted with that. Acid catalyzed synthesis of these, do you need to provide all the steps in the reaction? No, I typically focus on the overall picture. The mechanism, particularly for ethers, is good for understanding what's going on. It is not important to the overall picture. So, yes, if you just want to specify that you've got ethanol and you're adding acid, and you're going to have this reversibility error to give you the diethyl ether, that's fine. You don't need to write out the steps that you go with the H2O plus, and then you have nucleophilic attack by the other one, and then that loses its hydrogen. It makes it important for understanding how the reaction occurs. It does not do anything in terms of like affecting the overall picture of what's going on. So I would say for the ethers, no, you don't need to be able to write the mechanism. The overall picture is sufficient. So that's it for the questions I got today. I've got the chat menu open if you got any questions. Other than that, these aren't lectures, these aren't lessons, these are office hours. So please feel free to ask your question. And when I see them, I'll get back to answering them for you. All right, just got a question in the chat. With the alkyne elimination, it says that the HO is added for terminal alkynes to remove the hydrogen. If a terminal alkyne isn't created and we're writing out the synthesis, do we include HO even if it's not the terminal alkyne? You don't need to. In practice, the water is added to react. You never add like 1-to-1. You always add excess strong base because you want to make sure the reaction actually goes to completion. So you make sure your organic compound is the limiting reagent and you got enough base in there to ensure that it's all gone. Now, odds are your base is going to react with whatever the next step is. So I would add the water regardless, just because what's going to happen in practice is that you're going to add the water to react away your base so that your alkyne can be isolated. But particularly with a lot of the alkyne stuff, you're going to see water is added as a follow-up step. This is what's considered, what you'll hear pop up later in organic chemistry, what's called an acid workup. We're going to take our solution and we're going to add like 1 molar HCl to it to get rid of all the bases, to protonate any of the organic compounds, and just kind of make sure that like we don't get any surprise reactions down the road. One more question. For alkyne deals alder, what would be the best approach when doing the problems and kind of losing traffic and translating into the product? So same thing you did for original deals alder. So when we did the initial deals alder reaction, you had your diene, draw it out a little bit more simply, and you had your dienophile, and we did 1, 2, 3, 4, and the alpha and beta. And when we did the product, we had alpha, beta, 1, 2, 3, 4. And what we did is we just went through, and whatever was attached to 1 we put here, whatever was attached to 2 we put here, 3 here, 4 here, alpha here, beta here. If you're alkyne, you're just adding another bond. Oops, sorry. Got that backwards. So when you did deals alder with an alkene, you had 1, 2, 3, 4 alpha beta, with alpha beta being across from this double bond. And whatever was an alpha and beta, if they were cis over here, they were cis over here. If they were trans here, they were trans here. And you just kind of attach things around the circle. For an alkyne, you just create an extra bond between alpha and beta. And these will automatically be cis on the opposite side on this double bond. So that's the only difference between alkene deals alder and alkyne deals alder, is with alkene you end up with that one cycle hexene and you just attach things as you saw them on the starting alkene and diene. And then for alkyne deals alder, instead of having one double bond you have 2, and that second double bond is where your original alkene was, now it's an alkyne. And whatever is attached to alpha and beta, those are now on this side of the ring. But yeah, if you can do deals alder with alkynes is actually easier than deals alder with alkenes, because with deals alder with alkenes, you have to keep track of these groups being cis or trans in the starting alkene. For alkynes, whatever is attached to alpha and beta carbons, they're automatically cis because you're at a double bond. For final exam review, what would you suggest is best in terms of studying and doing good on the exam? I was just going through each unit and reviewing and doing the practice problems as of right now. I think that's kind of your best choice. I'm going to kind of give you a hint here on the final exam. It's not going to have much on terms of alkynes and ethers on it. So your focus needs to be more on the earlier materials. Yeah, test 1, test 2, test 3, and test 4 probably where a bulk of this final exam is going to come from. Again, maybe an occasional ether or alkyne, but definitely your efforts are better put on the earlier course material. Sorry to constantly cut off. I actually got somebody repairing a bathroom like down the hallway from me, so I'm gonna like keep cutting the camera off just so he can get work done. So if you understand the problems and know what you're doing for the most part, you should be fine. Yes, I would say that's a very good sentiment. There's only a handful of questions in the so the final exam are not questions written by me. They are written by collaboration with instructors. We're looking to change them this spring. Doesn't really do you any good right now, but there are a few questions on there I would argue aren't the best of questions. There are also a couple I would argue like they're just not well worded. But 30 questions, multiple choice. For the most part, you should be able to pass that exam pretty easily if you've been doing well in the course. And they're not all weighed. So you'll see when you look at the exam, but yeah, 30 multiple choice questions, and if you're understanding the material, you should be fine on the exam. There's a few that are a bit tricky, a few that are a little, I would argue, are kind of hard to understand. But again, please feel free to ask questions during the final exam if you need clarification on a question. Yeah, I would say you're going to do just fine on the final. All right, that seems to be it for questions today. Again, these are not lessons or lectures, they are office hours. So if you have questions, please feel free to email in advance, and I will see a lot of you for the last lab tomorrow.